in this video, we'll start talking about how we actually calculate most of our indefinite integrals. And this is by looking at the concept of the antiderivative. And what we do here is we're kind of working backwards from derivatives. So jumping into that, here's the concept. The idea is that we're working backwards from derivatives or from the derivative rules, and that will in turn produce what we call, an antiderivative. Antiderivative. So just anti as in kind of undoing or canceling, and derivative because it's working backwards from a derivative. So f of x is an antiderivative of little f of x if the derivative of big F of x is equal to little f of x. So if you want to think about the derivative, we do the derivative to find the derivative function. The antiderivative function is whatever we started with. And what you should note is there's an infinite number of possible antiderivatives of a function because the derivative of a constant is 0. So for example, if we have f of x equals 2x squared plus 3, one example of an antiderivative would be 4x, sorry, it should be 6x. That's also not right. It should be 2/3 x cubed. So going a little slow here, times plus 3x. So if we take the derivative 3, bring it down, we get 2x squared. Derivative of 3x, we get 3. I can also add 1 to that, and I get the same thing. 2x squared plus 3 plus 0. I can add 1 more. I can add 1 more. I can add 1 more. I can add 5. I can add 20, right? I can add any number to this, and all of this constant will drop out when I take the derivative. So each one of those, so 2/3 x cubed plus 3x plus 1, 2/3 x cubed plus 3x plus 2, plus 3, minus 15, anything with a constant, all of those are antiderivatives of 2x cubed plus 3, because in all cases, when I take the derivative of those functions, I get this original 2x squared plus 3. So to find an antiderivative, and ultimately we care about this because we're using them to solve indefinite integrals, first you're going to look at the rules for derivatives, and then you're going to try to think about how you would reverse the process. So for example, with the power rule. Now, if this was a derivative, we would reduce the numerator power by 1. So instead, we're going to add 1 to the numerator because we're undoing what we would do for the derivative. And then normally we'd bring down and multiply our function by n. So in this case, though, we want to divide by n. And then because we said that you can have any of an infinite number of results, we'll put this little bit on here called c, which is our constant of integration. And it's just to represent all of those possible numbers. And I realized I made a mistake here. This should be n plus 1. And you can check this because if we took the derivative, the n plus 1 comes down and those cancel out and go away, and we're left with just n in the numerator. So this is kind of, like we said, it's the opposite of what we've done before. This c right here is called the constant of integration. And it represents an unknown fixed value. So it's not a variable. C will never change. It'll be a fixed value for a given function. But because we don't know which specific antiderivative we want, we haven't fixed it yet. So if we want the quote-unquote simplest antiderivative, C is going to be 0. But like we had seen on that previous slide, any constant can be added. So we write this big C to represent that arbitrary constant that we don't know yet, that we'd have to get more information if we wanted to find a specific situation. In the next video, we'll look at all of the basic antiderivatives by just kind of undoing or backing up all of the functions that we've done thus far.